Okay, so let's begin. Today I'd like to give like a summary lecture of everything that I've been talking about over the last 4 days. I'd like you to start thinking and discussing and asking questions about the possible models of formation of binary black holes that we observed with gravitational waves, and models of discriminating between various scenarios. So I will organize and clean up all the slides that I've been showing, and they will be posted somewhere on the web page of this meeting, so that you will have some reference with some of the formula that I put there, and references to several scenarios and processes that work in there. But if I were to give a real short summary of what I've been talking about, is that then you have to, well, then there are the following processes. One is that if we have wind mass loss, then A times M is constant. If we have two then mass transfers, then we have two options. One, if the mass ratio is close to unity, then we should have something that will most likely be stable. Or if you transfer mass from a lower mass to a higher mass, the probability that the mass transfer will be stable is high. So if Q is much less than unity, it's stable. If Q is much larger than unity, namely if you transfer mass from a much more massive to a low mass companion, you will have something that is unstable. And here you can do any of this conservative or non-conservative treatments of mass transfers. Here you have to use something like the common envelope description of the mass transfer. And then there are processes like supernova explosions that can affect the orbits and can disrupt the system and have to be taken into account. So this is the whole 4 days in a very short summary. And given these things, you can basically build most of the evolutionary scenarios. And of course, you have to know how and then the 0th point is the radii evolution of stars. So for every star that you want to put in a binary, you can either use some approximate formula and evolve it and see what happens with its radius, and verify what will happen where and when it's going to enter a mass transfer, and what will happen with the system. So that's the short summary. But now I'd like to go into trying to answer or trying to show you what are the possible problems associated with answering the questions, where do binary black holes come from? So we have this set of observations, and we know that there are these binaries that contain black holes with the following masses. So some people have been saying that this is a surprise. I'm saying that for me it was not a surprise. I can show you that I've been talking for a while and writing papers about binaries in this mass range for a while, and that they, in my opinion, come out relatively naturally from the evolution of binaries with low metallicity. And there should be 4 objects, or 3.5. I added this one just a moment. Now, this slide you have probably seen many times. These are the masses. And in the X-ray studies, there are also, this is not a full picture, there are also objects two objects that sit in here. So I think that there is a continuous part that connects the X-ray and the gravitational wave population, and it's that these are not very distinct populations as might seem on the surface, just that there are different selection effects that let us see a different part of the black hole population with gravitational waves rather than in the X-ray studies. And in the X-ray studies, we mostly see objects in our galaxy, and in our galaxy we see black holes that have been formed from metal-rich material, so their masses are lower, and also it's easier to see. Well, on one hand, higher mass black holes will be brighter in X-rays, but on the other hand, the lifetime of the higher X-ray binaries will be shorter. So they will be visible for a smaller amount of time, and also because of the steep fall of the initial mass function, there is much less of the more massive black holes. On the other hand, with gravitational waves, our chances of seeing more massive objects are increasingly high because the sensitivity or the range of the gravitational wave detectors is roughly proportional to its mass. So the volume is proportional to the mass in the third power. So we are more likely to see more massive than less massive objects, and therefore it's easier to see binary black holes with high masses rather than, for example, double neutron stars, because we just don't probe a volume that is large enough. Now, this you also may have seen. This is the summary of the spin information from the observed black hole. So these graphs show the magnitude versus the directions of the individual spins. So this is the direction of the orbital angular momentum, and this is the probability density shading of the directions of the spins of individual black holes. And so in these two cases, I think very little can be said, except that the spins probably are not extremely high, that they are not close to unity. In this case, we have a quite good evidence for an intermediate value of the spin, which is nearly, well, close to alignment with the orbital angular momentum. And here we have a marginal evolution for marginal evidence for anti-alignment of the spin. So basically, there is an 80% or so of probability that it's anti-aligned, but so this is essentially a 1.5 sigma evidence for anti-alignment, and I would say that a result that is 1.5 sigma is not going to be, it shouldn't be really taken as a hard evidence of spins. If you look at the value of the effective spin, which is the mass-weighted mean spin of the two black holes, it is surprisingly close to zero, which in my opinion means that the spins of the black holes that we observe should be relatively small. If one of them was large and they had some, then the mean spin wouldn't be consistent with zero. And in this three cases, the mean spin is consistent with zero. Here it's not. It's slightly positive. But these studies are, I think, are quite important for identifying the properties of these black hole binaries and identifying what they really are. So I didn't talk much in my previous lectures about the spins of black holes, but maybe I'll do it later on during this talk. So now that we know that these objects exist, and you've listened to the lecture, here are, I think, the three major challenges in formation of these binary black hole systems. So the first is the masses, and I think that's not such a big challenge, but the question is how to obtain such masses in the normal stellar evolution. And I think no matter which, I will talk about different models, but no matter which model we take, we have to make these black holes in some sort of stellar evolution. So this is a universal question that, in my opinion, applies to all the models that we have. Then the second thing is the separation. If these objects are merging, they have to in spiral within the Hubble time. And yesterday, when you were trying to find the possible scenarios for formation of binary black holes, many of you have managed to obtain binary black holes, but they were on too wide orbits, and they were too wide to merge in the Hubble time. Yeah, so it is. This is a big problem, and you have to have some mechanism that brings them back together to a distance much smaller than the initial radii of the stars from which they evolved, because they start from stars of the masses of about 50, 60 solar masses or so. So two stars, and if the radii of the stars are proportional to the masses, then that gives you about a 60 solar radii for each star. They cannot be too close because they cannot go into the contact very early in the evolution, because then they would merge and form a single very massive star. So they have to be at a separation of a few hundred solar radii initially. But in order to merge, they have to be at a separation of a few solar radii so that they can merge within the Hubble time. So we need some mechanism to bring them in together and get rid of angular momentum from the system. Oops, I've been talking too long. And a third challenge is that we have the number, the expected rate, or the measured rate now, and I will argue that this measured rate is actually quite large. So we have to be able to find a mechanism that makes them efficiently and that is relatively easy to, the conditions that are relatively easy to realize in the universe, and not that we have some very fancy environment where we produce these things through very unusual and fancy processes. So currently in the literature, there are these 3 or 2.5 scenarios. So some people will not agree with my 2.5. So I've been talking mostly about standard binary evolution. So, and you more or less should have an idea how the standard binary evolution goes and how the standard binary evolution leads to formation of binary black holes. But then a big competitor is the evolution in globular clusters, and globular, I haven't mentioned in much detail for lack of time, for lack of my expertise in this field. But globular clusters are dense stellar objects where the density is several thousands of stars per, or even millions of stars per parsec cube. And in such an environment, it is, you also have binaries, but collisions between these binaries are quite likely. And if you have a collision between two binaries, you will form a metastable intermediate, for example, object containing of 4 stars, and because it's metastable, it will decay into either single stars or a tight binary and eject to other stars that may interact again with other binaries, and such collisions, such processes with exchange of companions will happen quite often. And in these collisions, it is very likely that the more massive, meaning black hole components of the binaries will be staying together in a single compact binary and will be ejected from such a collision. So there is quite high probability for forming binary black holes out of black holes that were formed and evolved separately before. And another mode for the evolution or for formation of the binary black holes or majors of binary black holes in globular clusters is that in globular clusters the black holes with single black holes will tend to sink towards the center of the globular cluster, and they can merge and form a single intermediate mass or much more massive black hole in the center of the cluster with the mass of 100 or a few hundred solar masses, and then you may have captures of typical 10 or 5 or so solar mass black holes by this more massive central black hole. So this is a different process from the one that we are seeing, but it's also a possibility, an interesting possibility for the formation of black hole binaries and the formation of black hole binaries as a mechanism. And then there is a model of so in globular clusters we overcome the problem of bringing the stars together by via collisions and via production or formation of the black holes in collisions where they evolve through and their envelopes separately, but then later on when they meet, they can form a tight binary, and we don't care about their history. Now, a separate possibility is this scenario that is called chemically homogeneous evolution, and in chemically homogeneous evolution, it's a model where you assume that the stars rotate very quickly, and because of very quick rotation, they mix their chemical composition. They don't form a core with lots of heavy elements and metal poor envelope, but the entire star consists of a chemically homogeneous mixed material. And one can show that in such case, the evolution of stars follows the radius evolution, it follows a different curve, and the stars don't expand, don't grow that much as the stars with cores and metal poor envelopes. So in this case, if you have something like that, if you have a binary of two very quickly rotating stars, you can form a binary at a small radius, and you don't have to worry about bringing them together, because they are initially very close, and they just stay very close throughout the evolution, and you overcome the problem by not allowing the stars to increase their radii. So I call it a 0.5 because this, in my opinion, is a variant of the binary evolution with a specific radius evolution. So here is my now short bit of arguments about the rates, and this is the arguments I like to make, because these are order of magnitude estimates you can make on the back of the envelope. The typical supernova rate in the galaxy, I think Nils mentioned 1 in 30 years. I will say that it's more likely to be 1 in 100 years. So we have 10 to minus 2 supernova per year per galaxy. The density of galaxies is about 0.01 galaxy per megaparsec cube. Yeah? So in a gigaparsec, which is 10 to 9, in a gigaparsec cube, which is 10 to 9 megaparsec cubes, we have 10 to the 7 galaxies. So if you combine these two numbers, the rate density of supernova is 10 to the 5 supernova per gigaparsec GPC cubed per year. Yeah? And for all of you, who like this type of calculations, you can easily check from this that there is a supernova in the universe once every second. So if this is the rate density of supernovae, then we know that most of the supernovae will make neutron stars, and a small fraction or some fraction will make black holes. So assuming that this is the supernova rate in the local universe, then I will argue that the rate density of formation of black holes is about an order of magnitude less than 10 to the 4 black holes per gigaparsec cube per year. Now we can compare this with the current estimate of the merger rate in the local universe, and it comes out that about 1 in 100 or 1 in 1,000 of these black holes ends up in binary black holes, in merging binary black holes. And I think that this 1 in 100 to 1 in 1,000, it's a lot, because we'll have quite a number of these black holes will be free-floating, so they are out of the picture for us. Some of them will be in wide black hole binaries. Some of them will be in black hole binaries that come in binaries with white dwarfs, like the ones that will follow the evolution of some of the say symbiotic stars or low mass X-ray binaries. So our current measured estimated rate here, rate density, shows that making these binary black holes should be something that is relatively common in the universe, and if you have a scenario for making them, you can't say that, okay, I will have an exceptional environment. I will do them, for example, I'll have central parts of galaxies where I have a black hole, and the black hole big black hole will act as a catalyst to make small black hole binaries, because such environments involve only a small part of the matter in the universe, and you will have to make the binary black holes with extreme efficiency to make up for this rate. So now on the maximum mass of the black holes. This is one of the initial final mass relationship models, which shows that what would be the black hole mass from forming from a star with an initial mass of whatever it is on the x-axis. And the main feature that you can see here is that this maximum black hole mass strongly depends on the metallicity. And this is due to the fact that if you take a star and you let it evolve, the more massive stars have very strong winds. And by the time they evolve their core, the envelope will be shed by the wind. Metallicity is high. If metallicity is high, there is lots of opacity in the envelope, and the winds are stronger, and you just blow off the rest of the matter, and you are just left at the end of the evolution with a core. If you don't have the strong winds, you have much more mass in the envelope, and at the time of collapse, you can make a more massive black hole. There is, this line, I think, goes too optimistically to the very high values, because it doesn't take into account an effect that is called the pair instability supernova. And the pair instability supernova is due to the following fact, that in the massive stars, you have high temperatures in the center, and once the temperature in the center becomes high enough so that you can start having pair creation, so you have lots of radiation pressure, you have lots of high energy photons. Once some of these photons can create pairs, this becomes a disastrous state for a star, because if you have photons, they provide pressure. They have lots of momentum. Yes, and if you let them annihilate and make a pair, an electron and positron have lots of mass in comparison to photons that have no mass, but they have little momentum. So the pressure suddenly drops. And so once you have a very high mass star with lots of radiation pressure inside, you cannot go forever increasing this radiation pressure, because this mechanism turns in, and if you do proper estimate, there is a limit that limits the masses of black holes to about 60 solar masses, assuming that this mechanism works. But the point is, with low metallicities, you can make black holes with the masses of 50 up to 60 solar masses. So let me now repeat what I've been talking about, the standard evolution of binaries leading to a binary black hole. This is the scenario that I discussed yesterday, or in short at the end of the lecture, but I'll just repeat it again. So we have two stars at the zero-age main sequence. The more massive star starts to transfer the mass onto the less massive star. it sheds quite a bit of its mass, and the mass ratio is exchanged. This one becomes less massive. This is now the more massive companion. So here we have a massive helium star that collapses to a black hole. We have a black hole of about 30 solar masses here, with a companion of 80 or 40 solar masses. And this goes on a very quick time scale. This is like 3 to 4 million years. And then we have a next mass transfer episode, which should be the common envelope. We make the binary come closer together and we leave just the helium star or the Wolf-Rayet star core of that star. There is a direct collapse, and you have a merger of two black holes after some 10 gigayears in this example. And of course, this is the most uncertain part of the whole scenario. This is the bottleneck of binary black hole formation, the standard binary evolution scenario, because this is where you shed the envelope. This is where you bring them in together. This is what the magical mechanism that allows to overcome this primary problem of having the two stars very close and nearby. So if you go through that, you are fine. You are then you form the binary. So the question is how to go through the bottleneck, and the answer is that the donor must have a clear core and envelope structure, so that the common envelope can eject the envelope and leave the core, because the star has a distinct border between the two parts. If the star is continuous, there is no way for the common envelope to stop, because there is no border in there. There is nothing to define that. Okay, this is the end of my envelope. Now we have a core with different properties, and it's there. And we have found that for solar events are likely to result in mergers. That for common envelope, for the solar metallicity, the stars they enter the common envelope don't have a very clear core structure developed yet, and therefore the binary black hole formation rate for solar metallicity is very low, or even close to zero. And now low metallicity really and it helps in several ways. One is that the black holes that are in this scenario here are more massive. For solar metallicity, this star will shed a lot of mass and will have a lower mass black hole here when it enters the common envelope. So the system will have to will have to decrease its radius by a much larger factor to have enough energy to eject the envelope. Second thing is that the low metallicity stars have lower radii, so the companion will have a smaller radius, and it will be, and that helps to overcome the common envelope. So here is an example of what we have here. This is the radius evolution of the two model stars with 30 solar masses initially. one at the solar metallicity, one at 10% solar. And so this is the nuclear evolution on the main sequence. Then we have this part is called the Hertzsprung gap, and then we have the evolution of a star with, with helium during the helium burning, and we don't consider the further evolution of the star here. But in this part, when the system enters the common envelope, enters the mass transfer in this part, it's most likely not going to survive it. In the case when we have low metallicity, this part is smaller, and it's more likely, so this is a log axis, that we will enter the common envelope in this part of the radius expansion, and that will make the probability by the common envelope higher. So this is another variant of the possible solution. So if we want to go to low metallicity, why stop at slightly smaller metallicity? Maybe we should consider the primordial initial stars that formed with zero metallicity in the early universe. At some point, at the redshift of 10 to 15, first stars appeared, and they appeared from the metal-free material. So this is another option here. So the population 3 stars are this elusive population that must have been there, but we don't know very much about. So for population 3 stars, we know that their masses were probably very high because they have evolved quickly, and if there existed low mass population 3 stars, we would see them even today, because this time scale of evolution of stars with, say, half solar mass is much longer than the Hubble time. So if lots of them were massive, they were. It's very easy to form massive black holes, but the amount of mass in the population 3 stars couldn't have been shouldn't have been too large, because if they formed the massive stars, such massive stars are emitting a lot of radiation that would ionize the matter, and such ionization of the matter should leave an imprint on the cosmic microwave background. So if we don't see that imprint of the cosmic microwave background, that gives us an upper limit on the amount of mass, on the total amount of mass that was processed by population 3 stars. If they formed binaries, and all of the stellar populations that we know formed binaries, then we need to wait 10 to 13 gigayears for them to merge. So either we form them in such a way that most of them merge now, and they haven't been merging before, or for most of the populations that we know, the merger time, delay time distribution is falling, like 1 over t or 1 over t to the 1.5, and we see very few mergers of this kind now. And of course, there are very few observational constraints on this population, because we haven't seen even one star like that. So most of the constraints or their properties come from numerical simulations, and numerical simulations are what they are. What you put in, you get out, and it's not really observational evidence. So I talked about the homogeneous evolution and globular clusters. So now, once we have a model of formation of binary black holes or binary compact objects, so we have something like, we know that if we start from some amount of mass, so we have some mass in stellar that we can make stars from, yeah, then we put it into this black box, which is the particular model for formation of binary black holes. So this is like the engine that changes the stars or mass in the stars into binary black holes. Then here we have some set of binary black holes that come out, and we have some of their properties, and these properties will be their masses and their decay or delay times until the until coalescence. Yeah. So one thing that we can say that you know, for each of these mechanisms we can define a quantity which is the efficiency of productions of binary black holes. So how many binary black holes we form per unit mass that we put into this box, into this engine. Yeah? That is a relatively robust quantity that lets us compare the models. And you know, I always say that suppose that you are an investor and you have a couple of million solar masses, you want to think you know, you have to choose which machine you put it in to harvest as many binary black holes out of the engine as possible and get the most of the return. And then you have the mass distribution, and you have the time delay distribution. So in order to find the local properties of the population of binary black holes, you need another ingredient, because you need the star formation rate history for this particular mechanism. So suppose that you say that you want to produce black holes with low metallicity star formation, star evolution. So you need the star formation in, you know, solar masses per megaparsec cube per year as a function of the redshift or time in the universe. And then when you can combine this information with that information, and for each mass you find, you know, for each black, for each moment in the history of the universe, you know that you produced so many stars per unit volume, per unit time, and some of them merged early, some of them there is a different time delay distribution, and from that you can find what will be the rate density in events per gigaparsec cube per year as a function of z, and it's probably going to be something like that, or depending on what the properties are. And currently we are essentially probing this tiny part of this, this tiny part of this graph, because with only a few detection we can, you know, the farthest detection goes out to a gigaparsec. A gigaparsec is about the redshift of 0.2, so all of these changes, the rate density with the redshift, are hardly observable at this point, but you know, they will be much better in the future. So now the binary black hole production efficiency. So this is this quantity. It's the number of binary black hole per unit solar mass, the production. So if we have Salpeter initial mass function, the initial mass function that falls off at minus 2.3, and if we assume that all of the black holes end up in merging binaries, then this gives us the maximum value of this efficiency for the stellar evolution with such an initial mass function. So its value is about 6 times 10 to minus 4. So we 6 times 10 to minus 4 per solar mass in the binary evolution. So if we look for the actual values that we get from simulations, so for the metallicity equal to solar metallicity, this is 10 to minus 7, and if we increase the metallicity, we increase the efficiency, but of course decreasing the metallicity means that we have much less of the star formation mass in the history, because this typical star formation rate history is related to metallicities, and if we choose only a part with a smaller metallicity, we go down here. So this is the same on the graph, which just illustrates that if we go to solar metallicity, the efficiency of formation of binary black holes drops like a stone. So if you want to form binary black holes in the binary evolution, to go to the regions with low metallicity. So this is the point. Now, you can increase, of course, this efficiency if you go to globular clusters. So this is my field line, and that's the line from the simulations by the Mokka code done by Mirek Giersch and Abbas Askar, where because you can match black holes that have had different formation history, and they formed here and there, but then they can go into a collision and form a binary black hole, and they don't have to be initially together. And so this way you can increase the amount of this maximum value and this the black hole formation efficiency, and it's getting closer by within a factor of a few to this maximum value for the assumed Peter mass function. So evolution in globular cluster helps by a factor of a few, but on the other hand, globular clusters constitute only a small fraction of the total matter in the universe. Now, properties of the distributions, the typical delay times are like 10 to minus t2 minus 1. So I think that now there is another point. If we have distribution of masses, and this is one of the multiple models that come in this paper by Dominic and Al, and I'm in this Al part. So with the models of mass distribution, they depend on many factors, but the main thing is that we don't really know initial, final relations, so we don't know a good translation between the mass of a star, its mass of the collapsing core, and mass of a black hole. There is very little information from observations that could constrain this. So this is a main factor that makes this uncertain. And I think that this uncertainty, which is also applying to the distribution of binary masses in clusters. So, for example, in these papers, they show that they can recover the observed distribution of masses in gravitational waves. But this is essentially, all of these binaries in globular clusters are formed from the same distribution of masses of black holes as in the field. So I don't expect them to be very much different. Some people are saying that in globular clusters you will have this hierarchical formation of black holes, and you should have higher masses black holes because you have a merger and a more massive black hole that will merge with another black hole. But this is only a very small fraction of the mergers, because most binary black holes that form in globular clusters as a function, as a result of a collision, will leave the globular cluster because they will get an additional velocity from the mix of a merger. And it's relatively easy to leave a globular cluster because the escape velocity from a globular cluster is of the order of 30 kilometers per second, which is, maybe 50 kilometers per second, which is only of the same order as, for example, our orbital velocity around the sun. So it's relatively easy to leave. Now, with population 3 black holes, here the models, so this is the pink line is the population 1 and 2 standard evolution model, and these two models correspond to two models that appeared of population 3 stars that appeared recently in the literature. So here all bets are off. There is, people are proposing really crazy modeling, and it's essentially, I'd say, there is no real constraint on what the masses in population 3 binaries should be, with one thing that, the continuous lines correspond to intrinsic masses. There is this line around here that cuts off higher masses because of the pair instability supernova. The pair instability supernova should apply to all populations stars, and if they work, we don't expect black hole masses in excess of about 60-65 solar masses. So in order to have higher masses than 60-65, we need some hierarchical formation, and that's much more difficult. And that would be one of the, if we see something like that, that would point towards the globular cluster origin of that particular binary very strongly. So here we have the details of what I showed you on the blackboard. So if we have the merger rate density calculation, so that's the formula. You have an integral over the cosmic time over the star formation rate, and you take the black hole efficiency in the particular model, and you take the probability of the delay as a function of time, and you integrate over all the past times. And essentially here, there are two limiting cases for this equation. One is if you have an old population, then the star formation took part a while ago, you can integrate the total star formation over there, and you can say that what we see here now is just determined by the delay distribution, and the value of the delay distribution at the current, for the time that corresponds to difference between the formation time and the presence. If we have a recent population, then the rate density is dominated by recent star formation, because most of the binaries have relatively short delay times, and then the number of binaries with longer delay times falls off steeply. So one thing is that in both of these cases, the rate density should increase with redshift. If we have a recent population, the star formation rate as a function of the distance increases towards the redshift of about 2 by a factor of about less than 10, and then it falls off. So the recent population, the redshift, the rate density should increase, and the same for the old population. So in order to compare these models, this is a graph that shows the star formation rate in a little bit reversed reversed way. This is the star formation, so this is the time from the Big Bang until today. This is the star formation rate in population 1 and 2. So these are the, this is the metal, contaminated matter with the metallicity above, say, 1% of solar. This is the star formation rate in population 3 stars. So this has happened at very early in the history of the universe, in the first, less than the first 1 gigayear. And the amount of the matter is limited because of, we have the constraints from CMB. And the blue line is an estimate of the formation rate, star formation rate in globular clusters. The globular clusters constitute about 0.1% of mass around our galaxy, but initially they could have constituted about 1 or 2% of the mass in the galaxy, because, and in the meantime, in the last 10 gigayears, they could have dissolved in the because they are not so well bound. So that gives you the following constraints: that integrated star formation rate for population 3 is only about 0.1% of what we have in population 1 and 2. Integrated star formation in globular clusters is about 1 or a few percent of what we have in population 1 and 2. Population 3 binary black hole production is most likely, efficiency is higher than the one for population 1 and 2 for the current stars. We only have very high mass stars in population 3, so we made relatively more black holes. So you can compensate this deficiency by making more black holes per unit solar mass. But we see only the very tail of the distribution of the delay times. This star formation happened 13 gigayears ago, and we had to wait so much time. So many of these black holes have merged in the past, and we don't see that we see them locally. And the similar arguments limit the globular cluster rate. There is less mass, there is higher black hole production efficiency, but also the formation of globular clusters probably happened earlier in the universe. And the globular cluster star formation history is not that well constrained, so for the globular clusters we may happen to have quite some globular cluster formation going on until today, but this is under dispute. So this, I would say, is an open question that has to be settled by more detailed observations and simulations. Here is my rate density calculation as a function of redshift. So this is one of the best fitting models that we have of population 1 and 2, and the local rate here is in this model this is about 200. So this is a high-end model of the that is on top of the O1 rate. For the reasons that I have said, the globular cluster rate density looks like this. The point is here that the globular cluster formation took part in this redshift range. Now, see, this is redshift, and the previous plot I have shown was in time, so you have to change redshift to time. And because of the normalization with the star formation rate and the and this globular cluster rate falls onto the lower part of O1. So I think that these two modes coexist, and the relative fraction really depends on what we'll have in how much star formation we have in globular clusters, how efficient is the low metallicity star formation in the population 1 and 2. And for the population 3, we have lots of star formation here at the redshift of 10, but then we have a delay, we only see the delay distribution of the rate here, and it falls down to be orders of magnitude below that. And there are papers that claim that population 3 is the dominant source of binary black holes now. I don't think it's true, and I think that people who write these papers mix a little bit the. I don't think that these papers are wrong. I think that people who write them sort of mix the low metallicity population that we have here in the magenta graph with these two. So in many cases, the differences between the models are more in the semantics and in definition of what people mean by various populations than by the actual physical mechanisms that operate. So one thing that you can see from here is that the rate should be increasing with redshift, but this redshift scale is quite generous. So in this scale, we see first two steps here. So I think that with the current instruments, detecting this variation of the rate with the distance or with the redshift will be extremely difficult. But if we have the next generation instruments that should see black holes up to the redshift of a few, we should see this top, this peak, and maybe, if there is a more efficient production of mergers from globular clusters, this green line can hop above the magenta line for the redshift of 2 or 3. That would be a very interesting result, but we need to see them at this redshift. So here is, can we, okay, so now let me go to verifying all of this. So if we have a mechanism for formation of binary black holes, this is, and this is a mechanism that should be a part of the binary evolution scenario. It's not that it can be invented completely out of the blue. It has to be consistent with lots and lots of other information, lots and lots of other observations. We have this scenario, and it's not that we just see this end. If we want to see this end, we have to see some sort of manifestations of the system when they are flowing through this graph. So what are these observations that you can do? So one is that this is my favorite. You should see stellar binaries, and it would be nice to see them in this stage. Yeah, because if we see them in this stage, we know that they have passed through the common envelope, which is the most difficult part of the whole scenario to pass. So once we come past it, that some about some things above it, but we know that there is a mechanism that brings it here, and that's immediately before being there. If we have common envelopes, we should also see this infrared eruptions, because if you eject, here we eject like 50 solar masses of the envelope mass, it's not going to be really quiet and cool. It's going to expand. It will be optically thick, but it will be cooling down, and it's going to be emitting in infrared for quite a while. It's not going to be, fading away on the time of days. It's going to stay there for a while. So we should see the remains of the common envelopes, and there should be much more numerous than the rate density for the binary black holes, because we'll have common envelopes for all the failed cases, and also the cases where we have a common envelope and we make a much wider binary. So in all of those cases, we should have an observational consequence of this. Okay, gravitational lensing can see, so gravitation, with gravitational lensing experiments, we could see only very wide binary black hole systems. So merging binary black hole systems which are very tight would be seen as a single object by the current, by the systems, but it's still very important to look for black holes in the lensing surveys. So also we should see this types of binaries. So we should see the black hole binaries with main sequence stars on wide orbits, and these objects should be detectable if they are in our galaxy by Gaia. In our galaxy we'll probably not produce the binary black hole mergers because of the metallicity, but we should have massive stars, and they should arrive at this stage. In the case of high metallicity, they will probably not pass through this stage, but we should see them here. So the observations with Gaia should provide us with some cases of binaries that are here. Okay, and I'm going now to spend last few minutes on trying to convince you that we know two objects that sit in this part of the graph. And these are two binaries. One is IC10 X-1, another is NGC300 X-1, and these are Wolf-Rayet X-ray binaries with 1 day periods. So we know that the donors are Rayet binaries with the masses of, and I'll show you why, of about 17-20 solar masses. They have the periods of about 1 day. And the point is that we are not 100% whether the companions are black holes, but I think that they are. So if so, they fit the picture. If not, then we should look for them. So let me just give you the information on what we see. So the point is that we see these systems, and they are, and for these systems we see the radial velocity curve, or at least we see what could be interpreted as the radial velocity curve. So if we have the radial velocity curves, this system also has eclipses, so we know more or less what the inclination is. So it has to be greater than 78 degrees. And if we have the velocity curve, we have the mass of the Wolf-Rayet star from its spectroscopy, and luminosity. And for this system, which sits in a nearby dwarf galaxy, the uncertainty in the distance, relative uncertainty in the distance is very small because we know that it sits in that galaxy. If it was in our galaxy, the distance measurement would be much more difficult. The only problem with this picture is that in these binaries, you can, what you have is, well, you have a Wolf-Rayet star and a compact object. And the compact object is an X-ray source, and and the Wolf-Rayet stars have very strong winds. So the X-rays are so strong that they can ionize the wind. So the winds are ionized, but everywhere apart here. The wind here is non-ionized. So when the binary rotates and you observe it from some directions, you see a mix of the ionized and non-ionized wind. And by seeing this mixture of the ionized and non-ionized wind, you can that can mimic the motion of the well, you can then you can see the variation of the location of some lines, which will be due to the fact that you see the ionized or the non-ionized wind moving in different directions in relation to you. So if you have an observer here, then this non-ionized wind is rotating, yeah? And you will see the non-ionized wind velocity change like this. And if that is true, then your variation in the velocity is not the orbital velocity, but it's the wind velocity. So if it is the wind velocity, then it has nothing to do with the mass function of the binary. This is not but with just the properties of the star. And you cannot infer anything about the mass of the companion. So this is this problem, and if this is the case, then we don't know what the companion is. But if what we see is the radial velocity, then the companion is a black hole. And here is the so if the Wolf-Rayet mass is in this range, the inclination is in this range, and the black hole masses are in this range. But no matter whether this is a black hole or a neutron star, it must be a compact object, and it's a system that looks like we want to see. It's a Wolf-Rayet star with a compact object companion, and the Wolf-Rayet star has a very short lifetime, and the Wolf-Rayet star will make a black hole in about 100 or 200,000 years. So this is a system that is an immediate progenitor of the of a compact object binary that is here. We are not sure that this is a black hole, but on the other hand, there are no evolutionary scenarios that would lead to formation of a, say, 20 solar mass Wolf-Rayet star with a neutron star. If we prove that it's a neutron star, then we have to revise most of what I have told you about the binary evolution. So there are two systems like that are very good hints that this part of the formation can be overcome, and that we can have systems here that will make compact binaries. So now to get to the final few things, we have this quite important information on the spins of the binaries. And I think that, in the literature and currently in the many discussions, people say, okay, in the case of evolution of formation in the binary evolution scenario, the spins should be aligned. So let me just show you what I think about it. So in binary evolution, there is very little place for the transfer of angular momentum onto the newly formed black holes. The first formed black hole is going to go through one mass transfer, that is the common envelope, and this mass transfer is very short, so you cannot accrete a lot of matter, so you cannot accrete a lot of angular momentum. So its angular momentum will have the direction and value more or less the same as at the time the black hole was formed. Then there may be some accretion onto the black hole from the wind of the Wolf-Rayet star, but this is not an accretion, hidden accretion disk. This is accretion from a wind, and in binaries where we have accretion from the wind, in neutron star binaries where we have accretion from the wind, we see that the period of the neutron stars is doing like Brownian motions. It decreases, so there is a random little transfer of the angular momentum. Moreover, this wind accretion phase from a Wolf-Rayet star to a black hole is lasting for a very short time. It's the lifetime of this massive Wolf-Rayet star, which is not longer than about 300,000 years. So also, over 300,000 years, it's not possible to accrete a lot of angular momentum, especially that you're accreting from the wind, and the accretion rate is not maximal. So the initial spins are likely unchanged, and the question is, what will be the initial spins? So the first argument is that if you form a binary, then you form it from a rotating cloud of matter. It fragments into two cores, and you make two cores that should have similar direction of the angular momentum. And it looks more or less logical, but there are measurements of binaries and their angular momenta that look misaligned. We don't know why, but these are the observations. So the initial angular momenta in binaries may be aligned, but they don't have to be aligned. So, if we look at the solar system, most of the angular momenta of the planets and the sun are in the same direction, but maybe there is more to it. And we don't really know if what would be the direction of the angular momentum of the black holes that form, because the black holes may receive small kicks. During the collapse, we can have some non-symmetric neutrino emission before the collapse to a black hole, and even small asymmetry in that will lead to may twist the direction of the spins. So I think that in general the spins may be aligned, but there is a number of mechanisms that may make it misaligned even in the binary evolution model. And in the globular cluster models, where we have the formation of binaries through dynamical interaction, there is no mechanism to make the spins align, so they should be completely random. Now, in the chemically homogeneous models, they should probably be aligned, and they should be large, because we want the stars to be rotating quickly to mix their chemical composition. But I think that same caveats apply as in the case of binary evolution, because when we make the black holes, we can twist the spins here or there. So I think that this is one of the ways to distinguish between the models and to find which model really operates and which is not, but I think that there is quite some work to be done, and I honestly think that the the models will be that what is operating, what we are seeing, is a mix of various scenarios that work. So, in summary, I think that the standard binary evolution can explain observed properties of binary black holes, masses, merger rates, merger times, and the current constraints on the spins. The current constraints on the spins just tell us that the spins are most likely small. And we don't know a lot about their directions. And I think that if they are small, it will be very difficult to, if they continue to be small, it will be very difficult to find out what are their preferred directions, because we will need very strong signal to noise for that. So this is a promising avenue, but it has quite a long way along that avenue to solve this. I think that we need to, in order to prove or disprove at least the binary evolution scenario, we need to place this scenario firmly into the realm of astrophysics. This is not an isolated scenario. It has to produce various other phenomena, and we have to see it, see all of this. And one of them is this example with the X-ray Wolf-Rayet binary. And we should look for more of these types of objects. Distributions hints at high numbers for binary black holes, much less binaries with neutron star. And I think that doing the mass distributions can constrain some models and can give us information about the formation, the mass spectrum of black holes that we form. The state density with Z will be an important thing. So distinguishing models, this will be, I think, quite tough, and that the discussions will continue for a long time. So with globular clusters, we have this misaligned spins, but if the spins are small, that's quite difficult to say, but we should also have the mergers with intermediate mass black holes happening. So the central higher mass black holes in globular clusters with the typical stellar mass black holes should be there. For the chemically homogeneous model, there is one more thing, that we should have the relatively equal mass ratios. So already what we are seeing is a little bit in tension with these models. And another thing is that we should search also for progenitor binaries. So we should see binaries that are rotating quickly and evolving homogeneously, and they have small radii. So we have to also place this scenario in the realm of standard observational astrophysics and see the progenitors, the stellar progenitors of this object. Okay, so I thought I would be quicker, but my time is up and there is not a lot of time for questions. But if you have some questions, I'll be happy to try to answer them.